properties of the world around us arise from from how atoms are connected to each other and how certain atoms are connected to each other, and really being able to see how that actually goes on the atomic level and really see how properties emerge and why that is. So really correlate the geometric structure of materials with their properties is something that I find absolutely fascinating. What is so interesting about this particular microscope that we use is that it not only allows you to image and characterize materials, but it also allows you to build materials atom by atom.
We can do that very simply. So we'll shift the CO molecule to here. So now we can see that the CO molecule is now where we want it to be. And like this, we can create any sort of lattice we want. You name it, we build it.
What I like a lot is that we are investigating things that nobody has ever investigated, and we can see and measure things on such a small scale. We can see how the electrons are arranged in their orbitals, and we can investigate new materials that would be extremely good for applications and will hopefully make the world more energy efficient at some point. And we are on the edge of that knowledge.
We know that this gas in this room consists of molecules, and they move and behave in certain ways from which all these thermodynamic properties emerge. There should be a similar story with black hole physics, and everything should emerge, the whole thermodynamics of black holes should emerge from an underlying microscopic view. So one of the questions that we have is, what are the atoms, so to speak, that make up black holes? So this atomic theory behind black holes must be very different. It should obey what is called the holographic principle. It was actually invented here in Utrecht by our colleague Gerard het Hoofd.
I really want to understand the holographic principle. I mean, we can formulate it in some way. We have a lot of examples of it, but I don't think that we have the right. I think we still lack the deeper understanding of it, the language to formulate it in a simpler way. So with Raimond, we are definitely interested in understanding these different patterns of complex behavior in the Quark-Gluon plasma by using the technique of ADS-CFT by mapping to a gravitational system. So there is a black hole in this gravitational theory in one higher dimension, in 5 dimensions, that corresponds to this phase of quarks and gluons.
We're now at a stage where macroscopically we can describe it, and now we want to connect it to really the fundamental individual interactions and what that means.
We have a common student, so he will be doing the ADS-CFT, the theory with me, and he will be doing experiment with him. So we really have a very concrete way of sharing the knowledge and just working together.
And it's quite amazing to see how much impact a student can have in this field. All the leading edge developments in theory and from experiments then come together, and you're always sort of at that forefront, hearing these things for the first time, sometimes seeing these things for the first time, and that's something which is just beautiful to see.